Hi, so this is a video editorial for the LeetCode Weekly Contest 512. The contest was decent. I'd say the problems were all right. Question 3 I liked. Question 4 had some good ideas, but overall it was like a standard problem as only. So like it took me less time to solve than question 3. Problems 1 and 2 were straightforward, so there's not much to talk about it. So as always, I'll be going through the problems presented in the contest in from problem 1 to problem 4, and after I have explained how I approached them, I'll attach a live solve section where you can see how I approach the problems in the contest itself. So moving on to problem 1. Problem 1 was basically we had to find the largest integer with the given digit sum. Basically, we are given n and s and we have to return the largest integer which has at most n digits, but the sum is exactly s. But since the constraints were fairly lax, which means n between 1 to 5 and s, the digit sum from 0 to this 100, we could do this. Basically, we had like, let's say, we were given some 4 digits, right? Let's say we were given n is equal to 4, so 4 digits. So the largest number can be 9999. So we can just run a loop from 0 to this number, and if our digit sum matches, we update our result. So this was my implementation. Basically, you just find the largest that value, and then from y is the current number, which would be the answer to this 9999. We get the digit sum, and if the digit sum is equal to the required digit sum, we update it, else we don't. And at the end we return the final answer. If we don't find anything, we return -1, so which is why res is equal to -1 at the beginning. This was problem 1. Problem 2 was easy, but the way it was worded was like fairly complicated. What basically, like, if I have to simplify what the problem statement says, we just have to merge these two arrays into a single array, and they are sorted based on their timestamp. So the first key here is the timestamp, and the second one is the value. So in case the what do we say? In case that is equal, the timestamp in both of these are equal, then we add them. So let's say there is not an example here, but basically let's say in array 1 we had some x comma x1, and array 2 we had some y not x1. One second. X comma x2. We had this comma. So we had this, right? So in the final array they would be merged to become x comma x1 plus x2. It would be like this. Another thing is, what do we say? This the input states that the problem statement states that the input is sort both of the inputs are sorted based on time. So based on this x, they are sorted. So this problem is kind of analogous to merging two sorted arrays into a single sorted array, right? But here we just have to handle a single extra case where we are merging the same values into this, and in case the value is not same. So let's say here we have 1 comma 3, but there is no 1 comma something in this, right? So in that case, we just take the next available value here. So this was my and this was basically the problem statement, and the constraints are n less than equal to 1e5, and the values are less than equal to 1e9, and obviously the input is sorted. So this is the standard code for merging two sorted arrays into a single one. If both of the indices are available, then first we get the merged value, which is the actual value, sum of the values. If it is equal, then we move both the pointers ahead and add the sum, and of course the timestamp itself. Else, whatever is the lesser one, we insert. And if only one is available, then we insert that itself. So this was Q2. Now moving on to problem 3. This was a nice problem. Basically, we are given two positive integers n and k, and we have to form a sequence of k. Like we are given n comma k, right? We have to form a uh, sequence of length k. The length is k, where all elements are positive, which means all elements are greater than 0, and their sum, which is sigma of the elements, is equal to n. It's strictly n, right? And we are also given another property that their product, the product of all elements, should be even, which means product should be a multiple of 2, right? Product should be a multiple of 2. Product not 2 should be equal to 0. We are given this, and we have to return the count of all valid sequences. So initially, and the constraints are obviously n is less than equal to 5v5 and k is obviously less than equal to n. Because since all numbers are positive, if k were greater than n, then there would be zero sequences. So yeah, this is the problem statement. Now moving on to my initial idea was to do something like with DP, we could maintain if big since the product will be even if there is at least one, if at least one element is even, that means the product will be even, right? That's a property since that even number would have a 2 in its factorization, and adding 2 to the total factorization of all elements would make the entire thing even. So we have to ensure that at least one element is even. So for that, I was thinking we could do some sort of DP, but that wasn't fitting within the constraints, right? So my next idea was, okay, so we know this, we can find the all sequences whose sum is all sequences of length k whose sum is n, and then all sequences of length k whose sum is n, and all of the elements are odd. And if we remove this, like from this is basically all, and this is the bad case, right? If all elements are odd, that means our rule is not being followed. And if our rule is not being followed, that means the sequence is bad. So if we do all minus bad, we would get the total result which we want. So for all for the so this is the idea of stars and bars. It's basically a combinatorics idea for counting divisions, right? So for visualizing this, we can assume like we have n boxes or n stars. We have n stars, and we have, let's say, k students. Let me draw something else for the students. We have k students here. Here n is 7, my bad, and k is 4. So basically, we have to allocate these 7 boxes to these k students, right, in this order. So for array 1, 3, 2, 1, which is sum is 7, the allocation would be this box would go to this, these 3 boxes would go to this student, these 2 would go to this, and the last would go to this, right? So this would make the array, basically the division would be like this, 1, 3, 2, 1. So these are the stars and these are the bars. So this is the basic idea here. So by using this, and every student should have at least one star, right? Since all elements are positive. So for this, you can basically prove this using combinatorics and factorial and stuff. It's not that hard, but I'd recommend reading up an article or something. So for this scenario, the number of sequences is n minus 1 c k minus 1. Right. So this is for all sequences, but we also have to remove the bad sequences. Now let's say after this we have some sequences remaining, right? Let's say this is the n minus k sequences we have given for counting bad sequences. My idea was, let's say we have given every student at least one sequence, which has to be done obviously. So now we have some n minus k items remaining. We have given n minus k items remaining. Now let's say we have these n minus k items, and every student already has one item. If this were odd, my claim is if the number of remaining sequences were odd, currently it's even. Let's say we add one to make it odd. Since we have already given every student one item, if this is odd, then its division would also be odd. So it would be like some even. There will be some even elements like grade less than equal to some like greater than equal to 0 even elements and one odd element. That's how this would become odd, right? And this odd element can go to the remaining odd element to form an even element. And if it forms an even element, then we would have at least one even element, right? And in that case, there would be no bad cases. So we ignore that. If so, this case we ignore where the n minus k is odd. But if n minus k is even, so which is this? Ignore this. This doesn't exist now. So the we can divide this. If n minus k is even, we have exactly n minus k by 2 boxes, right? Basically, the idea was, I'd reiterate, my bad. The idea is we already have given odd boxes, 1 box to every child, right? Now we have to ensure all of the every child has an odd number of boxes, and to ensure that we can only give them even number of this items from here. So because odd plus even would ensure it's odd, right? So which is what I did. But here we could also give a child zero box, right? All of this sum has to go, but we could also give a child a zero box. So like in the final solution, the one child could have one box, which would correspond to the number in this array being one. So you do another stars and bars here on this n minus k by 2 with the constraint that every element has to be greater than equal to 0 instead of greater than 0 like last time. So this was my solution. My implementation was fairly straightforward. This is just the factorial computation thing for finding NCR. This is the NCR function. First of all, we get the total cases. If n minus k is even, then we do this. X is equal to n minus k by 2 because we are only giving multiples of 2, right? The boxes. We can't give 3-box cluster. We can only give a 0-box cluster, 2-box cluster, or 4-box cluster. So basically, for to simulate that, we can do a stars and bars on n minus k by 2. Okay, so this is that x plus k minus 1, 3k minus 1. Here it is this, we are doing this plus because uh, uh, this constraint is not there. We can also give a child 0-box. So that was that, and we removed the bat from the total cases, and that is the result we return. So this was a decent problem, I'd say. Q4 was straightforward. It was easier than Q3, in my opinion. Basically, we are given a matrix of n cross m. I swapped m and n in my solution because I'm more used to n being the number of rows. The cost to enter a cell is this. To enter I comma j is I plus 1 into j plus 1. And we begin at this, and we pay its entrance cost, obviously. And then we can move to adjacent cells. Let me erase this. We are at a matrix. Let's say this is I comma j, right? We could move to an adjacent cell provided it exists, and after moving to the cell, we pay its entrance cost, right? But there is also a penalty associated with our movement. So for every even numbered action, so what happened is we moved to 0 comma 0. So this was move 0. So after that, the next move would be move 1, right? The next move or next action would be action 1, and action 1 is odd. So for action 1, if we move to the right or to the down, we don't pay a penalty, but if we move to the up and to the left, we have a penalty. And the penalty is provided by this. Let's say we are moving from I comma j, so the penalty is ij. Yeah, and so that was for odd numbered. So let's say we were performing an even numbered action. So in that case, these two, so left and up would have no penalty, but right and down would have a penalty. So that was the idea. And also we could also do one thing. We could also stay at the same cell. So since we are staying, the penalty, there is no movement, so no need to handle the parity of the move. But since we are still staying in that, we have to pay a penalty of I comma j, right? And every move we wait or stay, the action number increases by 1. So we have to return the minimum cost to reach the bottom right cell. So if I have explained this problem, you probably, like, if you are used to solving these type of problems, you would have understood that this is a straightforward Dijkstra's problem. Not that straightforward, but still like fairly straightforward. So looking at the problem statement again, we need to know the parity of the current move, right? To handle the cost, like it's either this or it's either this. So we need to know the parity. So parity, we also need to know the cell, obviously. So this would be our Dijkstra state, the parity and the cell. So at some state, what we can do is we can either stay at the same state. So we could do the parity flips by 1 and we stay at the same state, or we move. And for moving, we have some ni comma nj, and obviously this parity will always flip, right? So p becomes p or 1. We have this would depend on our current cell and how we move to the adjacent cells, obviously. And here, apart from adding the cost, we would also calculate some penalty based on this p or 1. So yeah, this was my idea. This was problem since once you know Dijkstra's, once you can model this as a graph and you have bare idea of Dijkstra, then this was just implementation. And into m is less than equal to 10 power 5. So yeah, my solution was this is basically just some random fluff. This is for swapping an m and n. And this is a function for telling if the thing is inside or not. So as I stated, our state would be parity and the beginning cell, right? So the move zero, initially our move was numbered zero for moving to 0, comma 0, and entry cost is just a function for getting the entry cost. I made this a separate function to handle the typecasting and stuff. Since we have this, right, n and m can be both. Wait, never mind. This is actually not required since m into n would be always less than equal to 10 power 5. But still, I just made it a function. I was worried that this might overflow, so but okay, that is basically this is our Dijkstra's distance array, right? So our Dijkstra state is 2. 2 is for the parity, which is 0 or 1 for the even or odd, and then which is then we have the index, right? So obviously at some index we get the state. If it is a suboptimal state, we could skip. Now either we wait. For waiting, the parity would still flip. Then we check the next end list would be the current cost, which is this parity. This would be cdisk as well, but whatever. And the penalty of staying at the same state, right? Not the same state, the same cell. The state would still flip since from P parity would go to parity or one. We check if it's optimal to move there, and if yes, then we do the Dijkstra's thing. And then we have the movement thing with the Dijkstra's distance array or direction array. You could make the direction array here. Then just check if the next index is inside. If it is inside, calculate the base cost and then add the penalty if it fulfills the rules. The reason I basically my distance array is like this. This is 0, this is 1, this is 2, and this is 3. So if our move is odd, that means and our distance is greater than equal to 2, which means we are here, right? For odd, this would give us a penalty, and for even, this would give us a penalty. So in either of these cases, we add the penalty, and then if we check, we can do the back first thing. If yes, then we push it. And at the end, the result is either at the even parity of the final cell or the odd parity. And you can just return the answer. Yeah, this was my editorial screencasting. Uploading after a while because I've been handling with some moving stuff. So yeah, as always, I'll attach the live solve section after this so you can see how I approach the problems in the contest itself. And feel free to comment if you have any queries regarding the explanation and such. All right, bye.
क्या है? 1 पे 3 है, 1 पे इधर है नहीं, तो 5 कहाँ से आया भाई? क्या है ये क्या है? Hmm. At least one event should be there. तो ही वो And minus 1 1.